In this video, we work through 3 example mock questions on differential equations using separation of variables. These types of questions are, as you can see from the 3 examples, they're usually given in a set of equations with dy dx, and then some y and x in a multiplicative form. In that sense, you see product or divisions of these expressions on both sides of the equation. And if you examine the questions, there are a few requirements. For example, the first one here says give your answer in exponential form. So that indicates that you probably will have a log at the end, and then you need to convert that back into exponential form. The third example here also says remove all the logarithms from your solution. So is the middle one. And the middle question here has one more step. Given an initial condition, so y equals 2 when x equals 1, show the particular solution. Okay, sometimes it might be asking for the particular solution as opposed to be proving it, which will be a little bit harder because you don't have the final expression to work towards. Okay, without further ado, let's get started with the examples. This block on the side here is the formula that you will have on your formula sheet. It's not everything for integration. You will still need the basic one, which is when y equals to a x to the n, your integral of y would have to equal to the constant going in the front, and then you raise that power by 1, divide by the raised power. So you will have to remember this basic integration formula. Okay, for this question above, the first step is to separate the variables so that your y and dy is on one side and x and dx on the other side. Notice you will have to have the dy and dx on the numerator, so on the top, not the bottom, because otherwise you cannot integrate. So the dy here is on the left. That means I'm going to move everything related to y on the left side and everything related to x on to the right side, because if I multiply dx on both sides, then dx can go to the right side on the numerator. Okay, so let's just keep all the y's on the left side, y minus 3 dy. And if I'm multiplying a dx, that makes the right side having the dx. Okay, and then I don't want the x on the right. I don't want the x on the left side, and I don't want the y on the right side. So I have to now, so the first step, let's just write it down, times dx on both sides, times dx. And then second step is I divide by x and divide by y on both sides. That would give me y minus 3 over y dy. So that's gone, but the y is divided, equals, the y is gone, 4 here, and then x is also divided, so 4 over x dx. So now everything is separated. With that done, we can just simply integrate both sides. Put integral sign. The left side, I'm going to simplify it first before I integrate. So y minus 3 is y divided by y is 1, and then minus the 3 divided by y dy. And on the right side, nothing to be done. So integration, if you look at your formula, other than the normal basic integration that deal with powers, the special one is 1 over x, because if you raise that power by 1, you get 0, because 1 over x is x to the minus 1. So that wouldn't actually work with the power formula. So the special integral answer would be log of x. And technically, there is a absolute sign around here. But there's mixed sentiment in the field about whether to include it or not. It's mathematically accurate to have an absolute value sign. But absolute value functions are notorious to deal with. You always have to separate the function into 2 branches. If it's greater than 0, this happens. If it's less than 0, the other thing happens. So in the applied world, a lot of times you just examine what the situation is and decide whether your value is positive or negative, and therefore get rid of your absolute sign. So for this module, if in your first step you had included the absolute sign and then sort of dropped it in later steps, that just demonstrates that you know that the integral of 1 over x is log of absolute value of x. That would be sufficient. Okay, so let's do this one. On the left side, integral of 1 is basically 1 times x to the 0th power. So the integral of that is 1 times x. 0 plus 1 power divided by 1, and that would equal x. Okay, so integral of any, actually k, that's a formula, any constant is just k times that constant. So here I have y, there's the integral answer, and then minus the 3 is a constant, stick in front, log of absolute value of y. And then that equals to 4 is the constant in the front, and log of absolute value of x. Okay, because this is indefinite integrals, each side would have a constant, and to combine those constants, you will have a one constant c. So if you have a c1 plus c2 and then move the c1 to the other side, you will have like a c2 minus c1, but because it's any constant, it doesn't matter if it's just a single symbol to represent that. Now, that is solved, but it says it wants your answers to all be in exponential form, so we have to try to get rid of the logs. In order to get rid of logs, at this point, if you want to drop your absolute value, that's totally acceptable here. In order to get rid of logs, we have to take an exponential. So take exponential on both sides. You will have e to the y minus 3 log of y equals e to the 4 log of x plus c. So just put the equation into the exponent of the exponential function. Now we need to use some of your knowledge on power index calculations and logs. Remember, anything to the index two numbers multiplied, added together equals to the separate a to the m times a to the nth power. So basically, if you have m sets of a's multiplied together, multiply n sets of a's, and together it's m plus n sets of a's. So to use this formula on here, I would have e to the y times e to the minus 3 log of y equals e to the 4 log of x times e to the c. Normally, if you notice that e to the c is also just a constant, so we'll rewrite that as let a equals e to the c. So replace that constant with a. But you notice that you can't do much things here unless you do some manipulations in the exponentials and logs. So we need to invoke our knowledge on logs. So remember, logs and exponentials are opposite calculations of each other. So e to the natural log of a number just give you that number back because they're like opposite calculations. In our formulation, it's not quite like that yet. So the other thing we need to know is that k, a constant, times natural log of a is actually equal to log of a to the kth power. So if you combine those two formula, you will have e time to the power of k constant times a natural log of a would equal to e to the natural log of a to the kth power. Therefore, it equals a to the kth power. In here, we have two forms that look like that. So copy the e to the y down. The second part is going to be changed into e to the natural log of y to the minus 3 power. So because our k here is a constant in front, that becomes the power of the y. And same thing happens here. E to the x to the 4th power, because that's the constant 4 in front of the log, times, we said we're going to change that into a constant a. Okay, now all the logs can be gotten rid of. So e to the y times e, no more e, sorry. Log and e cancels. And we have y to the minus 3 power, that equals to the x to the 4th power, and times the constant. So this is the end of the answer in exponential form. So there's no more logs left. You might find the step between the yellow highlighted answer that has logs in from here to the green expression a bit tricky. Truth be told, if you got the yellow answer, that's the bulk of what we're looking for in solving this question, that you're able to separate the variables and integrate. Now, going from log to exponential, that is the last step, so giving your answer in exponential form, but that's got fewer marks, to be honest. So the main thing is you're able to do the first bit. In order to do the log to exponential bit, you will need to remember some of your log and exponential function formula.